All right. Going to start. Thank you everyone for coming. It's really good to see that many people coming tonight. So I'm going to give you a quick introduction on the 2 days. We've got tonight and tomorrow, where we'll be talking about changes expected for the area, and also start the discussion around adaptation and principles around that. So tonight, we've got a few people from the Regional Council and a few councillors. Got Councillor Moon, Councillor Wilson, Councillor Scott, Councillor Forbes, and
Councillor Wicks on the way.
She's about to walk in, isn't it?
She likes big entries. Keep her on embarrassing.
we also have Gavin Palmer, General Manager Operation, Tim Van Woorden, Natural Hazard Analyst, Asma, Ben Zafar, Communication, and I am Jean-Luc Payan, Manager Natural Hazards. I think everyone, and Councillor Glenn from PRDC. So tonight, Professor James Brasington will be talking about braided rivers and what they do and what to expect them to do in the future. But Councillor Forbes will introduce James properly. So tonight the idea is to talk about changes and how we assess those changes. It's going to be technical discussion, but feel free to ask questions. Today is about the time to ask questions to understand how we try to better understand those rivers. Tomorrow will be a different format. It'll be a drop-in session from 2 p.m. to 7 p.m. It'll be in that side of the hall. And the purpose of tomorrow is just a reminder of the first session. For some of you who came to that first session, but it's a step forward. So the first session was about natural hazards, what we can expect in the area, and summarizing that. Next, tomorrow will be about future changes to the river, to the morphology, how the river gravel bed is going to change, how climate change is going to affect that. So that's one part of the discussion. But the other part of the discussion is really starting talking about adaptation approaches. We're not going to talk about the detail, but it's start to talk about the high-level approaches. We've got another session in about 6 months' time, where we'll be collecting the information, taking into account the discussion of tomorrow, to really start talking about the detail about adaptation. What that will mean for GLENORCHY, for GLENORCHY, for that area north of here, basically. And I just want to acknowledge
sorry. Well, I had to check in the motel because I didn't know what the lady would do. She'd lock me out and I'd have to camp here at the hall. So I apologise, I'm from Middlemarch. Thanks for having me.
And actually, I forgot also, we've got Nick Rogers from Tonkin and Taylor. He'll be here tomorrow also to assist during the discussion. So let Alexa introduce James. And thanks again for coming.
Kia ora koutou, and thank you so much for coming. It is awesome to see this turnout, to hear James and to set into context the thinking that we have to do and how we approach our rivers. So James Brasington is an environmental earth scientist who knows a lot about rivers. He's well known for his development of theories and methods to quantify and predict the dynamics of river systems. If I've got this right, and you can correct me later if I'm... There's a whole lot more in this bio, but not words that were easily pronounceable. He's a Professor of River Science and a Director of the Waterways Centre for Freshwater Management at Canterbury University and Lincoln, and that's among a whole pile of other things, but those were the ones that I felt were most important for us. He has nearly a quarter of a century of research experience. Doesn't look old enough, but there we go. Research experience in river science, been doing it since you're 6. And his particular expertise is in flood hazards and sediment transport. James has got a record of research on the REES-DART going back to about 2008, and he's led at least 3 international projects on understanding the form, character and evolution of these 2 rivers. So he knows about this area and not bringing in stuff from another river. It's just these rivers. So as we look to understand more about how we can live with our rivers in this area and how we want to do that, James's talk is really timely, and thank you to our team, our ORC team, for bringing James and putting so much effort into making sure that we do understand the context really well. And that when I asked John Luke about the last session, tomorrow's session, and the next one that's coming, and he said the next session is going to be about the detail of a plan. I said, but not a plan we've written. He goes, no, we haven't started. We're just collecting all the information, and so it's a very emergent process. So it's great to have James. Thank you.
Thanks very much, Alexa. And kia ora koutou. Well, it's a great privilege to be here. It's lovely to be back in Glenorchy as always. And as Alexa alluded to, I've got a bit of a history with the area. I've been working here now for some time, shall we say. I wasn't 6 when I started. Sadly enough, I'm going to hit 50 this year, which is still resonating. But anyway, so yeah, I started working here back in 2008 and bringing over teams from then. I was at the University of Wales. At Aberystwyth, on the far side of the world, and here 12 years later, 13 years later, something like that, I now find myself in a position at the University of Canterbury, which was probably all part of a big long-term goal in many ways, and it is great to be here. But it's meant that I've been able to keep a legacy of work running on the catchment that we sit at the foot of here. And what I really want to do today is provide a little bit of context that outlines some of our understanding of the fluvial hazards that we are posed with in the townships here at Glenorchy and over the water there in Kinloch and the surrounding communities of the top of the lake. It's a dynamic environment, as you know well, and what I'm going to try to do today is give you an insight into some of the reasons why we expect some of these problems to become potentially more severe as we move through the 21st century. But I'm going to do that really by trying to bed down some of the science that we've learned over the last 12 years, very much as a means to try and informing that risk assessment that we're gradually developing here. I will try to keep things at a level which is accessible to everyone. If you think that I'm not, just wade in and tell me to stop and ask me to explain something, okay? I'm very happy to be interrupted, stopped, and challenged wherever you think's appropriate. Okay, so I'm very happy for this to be fluid, and of course I'll take any questions at the end as well if people would rather reserve them till then. So I entitled the talk here, Living with Rivers on the Edge, which we always talk about New Zealand being on the edge, and we're on the edge of a plate margin. That creates a context here which pretty much underpins a lot of what happens from a physical perspective when we're dealing with natural hazards in New Zealand. But I'm specifically going to be talking about the fluvial hazards. Now, you don't need me. You guys live here. You live the experience of this. And you know that Glenorchy has a very unique, what we call a hazardscape. It is an environment which is challenged by a whole series of seismic, mass movement and flood hazards, many of which are actually coupled together. That means that there can be triggers from one event that can cascade into another event and so on down through the system. So, for example, one of the kind of classic concerns that we might have in this area is the effect of seismic shaking associated classically with an alpine fault earthquake. While that's creating all the associated problems of liquefaction that we might experience down here in the township, it could also be setting in train landslide dams up, for example, in the Buckleburn. Those landslide dams, if they occur at times of heavy rain, may actually then get breached and swept through, creating a significant debris flow hazard. So one event can trigger another. And this is a problem that we deal with in environments like this. And these processes might often be quite distant from each other. Heavy rain in the headwaters may create landslides that may create flood hazards downstream some days later from the initial triggering event that occurred. So it's a very complex environment to try and assess all of these cumulative and compounding risks that the communities face. What I'm going to focus on today, specifically then, as I said, are the fluvial hazards, by which I mean those associated principally with the Rees and the Dart rivers. Now, these are probably not I think it's arguable to say, the most catastrophic threats that the township faces. I'm sure many of you who have read documents will have heard stories of large tsunamis potentially within the lake that could create flood waves that might be anything up to 5 or more meters high as a potential significant threat to the environment. The issues associated with seismic shaking, of course, and liquefaction and lateral spreading are major environmental hazards that the township faces as well. But while fluvial hazards may not be the most catastrophic potentially, they probably are the most frequent hazards that the township, both this side and the other side of the lake, must deal with. And those hazards are manifesting risks to life, risks to property, and of course risks to the critical infrastructure that supports the environment, the power, the roading, and the water distribution networks. What are the risks? Well, the risks, I'm not going to talk too much about this in many ways. These are fairly obvious risks, I suppose. It's direct inundation from water, but also swift water. And that's something that I think perhaps the township hasn't experienced so much of, and one that we need to think about, particularly if we have outbreak floods, a theme I'll come back to later in the talk. There are also risks associated with swift water of entrained debris, both sediment and, for example, large logs that might get carried through that water. And they again pose significant hazards both to property and to life. And then, of course, the other perhaps slightly more subtle but nonetheless very significant problem is associated with stream and bank erosion. The threats to Kinloch Road that many of you will be familiar with now, those of you who have crossed over the water and tried to drive down the gravel road on the other side will realise that the river is beginning to encroach very rapidly on the road, posing a significant risk to that critical artery for the area. So there are significant hazards, but what perhaps differentiates the hazards from the rivers, particularly the Rees and the Dart in this context, at GLENORCHY, is that these are hazards that we have good reason to expect to increase in both their frequency and their severity as we move forward into the 21st century. So whereas, for example, we tend to think of earthquakes having a more or less constant overriding probability of occurrence, effectively similarly with landslides, we tend to treat these as what we call random or stochastic events. There are good reasons to expect these kinds of fluvial hazards to increase in probability as we move through the coming decades. They are, the buzzword in statistics here is they are non-stationary hazards. The hazards where the baseline risk is gradually elevating as we move forward in time. Why? Okay. Well, the reason for this is that we're in a landscape which is far from equilibrium. What do I mean by that? We tend to like to think that landscapes are forever constantly fluctuating, but never really on a trajectory of change. That idea of the beautiful landscape that's more or less always in harmonious balance. Well, we have two major drivers of change in this environment that challenge that hypothesis. The first is that we have extremely good scientific evidence now that climate change is not only occurring, but is set to intensify as we move through the 21st century. Okay? The projections of what will happen vary dramatically depending on how we as a global community respond to that threat. But nonetheless, by about 2040, we have every expectation that this is already sealed in stone, that our average temperatures in this part of the world will probably increase somewhere from 0.5 degree to 1.5 degrees over that next 20 to 30 years. By the time we reach 2090, there's good reason to imagine that if we do little to combat these challenges, our temperatures could be as high as 3.5 degrees higher. Okay? 3.5 degrees higher means that we will generate significant increases in winter rainfall. So winter rainfalls could rise by anything up between 20 to 40%. And in particular, intense storms, those are storms with over 25 millimetres occurring within a day. Not always intense feeling on the west coast, of course, but in this kind of environment, that's still a significant storm, are the kind of events we expect to increase with significant rises in probability. In combination with increased hot days, reduced frost days, reduced snowfall, and particular increased winter rainfall, there are expectations that the flood flows on our rivers the mean annual flood flow, so that's, if you like, the average major flood that we get on average once every other year, could be as much as 100% higher than it is today. Okay? So an increase in the frequency and severity of flood events that are capable of presenting significant hazards to our environment and also changing the background environmental dynamics of the catchments here. The second and perhaps more subtle change that is less immediately evident and a little bit more complex to unravel is that we're in a catchment where the riverbeds, particularly close to the township here in the delta environments, are beginning to aggrade and have been doing so, well, not beginning to aggrade, have been aggrading for long periods of essentially geological time. Okay? The effects of that are now beginning to become manifest. So we're talking here about a build-up of riverine sediment. A build-up of riverine sediment that ultimately reduces the cross-sectional area of the channels that are carrying those flood flows, also reducing the gradient, the slope of the river, and in combination what that does is it reduces the ability of the river to convey the flood that's being generated in the upstream catchment. If we reduce the ability to carry the flood, we increase the probability that that flood will overtax its banks and find another route along a steeper gradient that may take us into harm's way. Okay? So these are the background drivers that are setting the scene for how this environment is going to change over the next 50 to 100 years. Why? Well, I'm not going to talk so much about the drivers of climate change. I think we're probably pretty familiar with those. But to understand why we're living in an environment which is degrading, a landscape which is out of balance, we need to look back in history a little bit. We're in an environment here where over the last 2.5 million years, a period geologically we call the Quaternary, we've had repeated warming and cold periods that have led to major glaciations that have taken hold in the Southern Alps. And there have been at least 20 major glacial periods where ice has extended dramatically over the Southern Alps, stretching out, developing large valley glaciers that have carved these great big U-shaped valleys that we see in the Southern Alps. And the Wakatipu Glacier carved the environment we're living in here today, probably some 1,000 meters above us, around about 35,000 years ago. Okay? So this is an enormous pattern of environmental change over what is geologically a relatively short period of time. So these great big deep valleys have been carved, and you can see here the Wakatipu Glacier will have extended all the way down to Kinloch, spreading out into the Von Valley, and then down across towards the Crown Range. The little remnant of that now is less than about 5 kilometres long. I'm sure many of you have sometime in your lives been up valley to see that. That process of deglaciation in this part of the world began around about 18,000 years ago. And as the glaciers began to retreat, the Wakatipu Glacier began to retreat, we developed the formation of the large Wakatipu Lake that you now see today. Okay? That began, as I say, around about 18,000 years, and it has been impounded by a large series of terminal moraines. So these are the sediments that the glacier pushed forward. The large complex at Kinloch is the main moraine that impounded the lake originally, and then we've had subsequent...
Kingston.
What did I say, sorry?
Kinloch, you meant Kingston.
Kingston, sorry, you know that.
Yeah.
At Kingston, way down valley here, but also then we've got secondary terminal moraines in places like Frankton and on the Von, which also created barriers to lake drainage. Now over time, as the rivers cut down through those terminal moraines, the lake levels have adjusted. The lake here has probably fallen from a maximum height of around about 360 metres, and that equates to the height of the terminal moraines down at Kingston, not Kinloch, and progressively down cut and then being rerouted to where the lake outfalls now down the Kawarau River and down into the Upper Clutha Basin. So there's been significant attempts to try and map out what's happened in this environment, and we've seen classically in your own environment here, the Bible terrace. The face of the Bible represents the leaves of the strands that the lake levels, as they gradually receded, have left in their wake. And there are now, we recognise, probably some 10 different shorelines, composite, reflecting that pattern of gradual fall of the lake, as the lake fell from a height of around about 360 to 309 metres. What does that mean? Well, it means that the lake was probably some 10,000 years ago significantly far upstream from here, extending all the way, probably connecting up to Diamond Lake and beyond. So a significant shift in the pattern of the proglacial drainage, and that's been mapped extensively across this basin. So we're living in an environment which is essentially very, very recent. It's, in geological terms, a very, very young landscape. What that brings with it then is an extremely high rate of erosion. And when I say high rate, I mean globally high rate. Some of the rates of erosion that we record in this area are amongst the highest in the world. They come from that legacy of glacial erosion, which has oversteepened the landscape, creating extremely a large number of extremely steep slopes that are subject to gravity and at risk of failure. They're also being continuously uplifted by the plate collision between the Australian and the Pacific plate, and in this part of the world we're going up at somewhere in the region of the upper headwaters around about 5 millimetres per year, again continuing to oversteepen the slopes and reduce their stability. And those same processes of uplift then get in the way of the roaring 40s, driving very, very high rates of rainfall falling in the upper headwaters here. And in the westerly margins of the catchment, we could well be looking at precipitation rates of over 5,000 millimetres a year. 5 metres of rainfall a year, the height and sum of this roof. Okay? So this is an environment which has got some really significant global processes driving high rates of erosion. The landscape we talk about in geomorphological terms is what we then mean is a paraglacial landscape. It's a landscape which is relaxing, it's an interesting geomorphic term, as we evolve away from the last glacial maximum, and it's one then which is characterised by a very high frequency of active landslides and retreating headwater glaciers, which are releasing large amounts of sediment that the rivers can then mobilise. Essentially, we're in an environment here where the amount of sediment available to the rivers is essentially unlimited. Okay? There is more than enough sediment to keep these rivers busy for the rest of their lives. Okay? They have an amazing amount of material that they are challenged with to transport down through the system down to the lake at the bottom of the catchment. Essentially, then, we have more sediment available than the capacity of the rivers to transport it. And that's really perhaps the most important term here. The system is what we call in geomorphic terms transport limited. The only thing stopping us transporting more sediment is enough flow to do so. And now begin to connect the dots. If we're now looking at an environment over the next 100 years where the frequency and severity of storms is going to increase, we're going to increase the transport power of our rivers, which is going to increase the transport capacity of the rivers and therefore increase the amount of sediment they're going to transfer down into the system. Now I'll come back to that. I'll wind our way back as we go through the talk. So we're living in a landscape which is essentially a dynamic or a living environment. Yeah? Our valleys are infilled here with extensive fluvial sediments. The way the rivers have adjusted to manage that high sediment load is to braid. Turns out that braiding, despite its beauty and complexity, is actually also the most energetically optimized way of transporting large amounts of sediment. Okay? When you look at some of the boreholes that have been carved down into the valley, they suggest that these sediments are coarse gravels, we have coarse gravels in those sediments to depths of at least 50 metres, and I suspect, were we able to go a little bit deeper, we may find those fills going down some 100+ metres. Okay? You're in an environment which has been degrading, not just in the last 10 or 20 years, but one which has been doing it now continuously since the end of the last glacial maximum. In the lower reaches then, as the lake has drained progressively to 309 metres, the rivers have come together to create this enormous alluvial delta, one of the signatures of not just this area, but of course New Zealand. And that delta is a delta which has been advancing over the pattern of recent colonial settlement. Now, there are photographs dating back to the turn of the 20th century that show that the remnants of the lake up against the township in the area that's now left as the lagoon. What we see the river hard against the true left or the eastern valley wall of the system at that time. The first really good scientific data we have on how the river has adjusted comes from the earliest metric aerial photography that was flown over the region in 1937. And if you compare the pattern of the Rees, at least in this picture in 1937, to a recent aerial photograph from 2018, you can get an idea of just how rapidly the system has begun to adjust over what is just around about an 80-year period. So at this time here, I've shown for reference the pattern of recent channel change, and we'll talk about how we've developed that map a little later as well, shown by those patterns of blues and reds, so showing the active course of the river in the last 10 years. But if you literally just compare the two images here, you'll see that we've got something like a 400-metre western migration of the active channel bed over that 80-year period. This is an environment which is changing very, very quickly. Now, where I come from in Wales, rivers don't change by 80 years in a couple of thousand years, 80 metres in a couple of thousand years, let alone 80 years. Yeah? So 400 metres in that short period of time is an exceptionally high rate of channel adjustment. And actually, if we go back a little bit further in time, there's good evidence to suggest that the river's been all the way to the eastern side of the valley and back across around about a 1.5 kilometre bend over the last 100 or so years. It's a river which is flip-flopping, adjusting and shifting its position over time. We can quantify the rate of advance of the delta. It comes out at around about 120 metres over the last 50 years, which represents around about 2 to 3 metres per year. Okay? So this is a process which has been continuing over the recent pattern of human settlement here. Okay, so I said I've been here for a while, and we've been working with a range of different approaches to try and understand how their system has been changing, using a range of new technologies and new approaches to kind of shed light on the riverscapes that we're looking at here. And we've been doing this in a variety of ways, and I want to try and showcase how some of the science that we've gradually been unpicking over that last 10 years can lead to new insights on how this system behaves and how the landscape has evolved, and then the lessons we can learn from that to point to how it might adjust as we move into the future. And there have been a range of different technologies that we've used here that are really giving us a new opportunity or new perspectives on the landscape. The first is that we have Earth-observing satellites now that have been up in space now since around about the early 70s. These are giving us really high-quality data that is reproducible and quantifiable to show how the landscape has changed over now roughly a 50-year period. That's an unparalleled environmental legacy to actually observe how this system is behaving over decadal timescales. Some of these space technologies available to us now are getting finer and finer and finer in terms of the detail we can see from them. So whereas the kind of Landsat series of satellites that were launched back in 1973 put a kind of 80-metre window across the world, that was the size of the observing pixels that we could generate. Now, the new generation of space technologies are bringing us down to sub-metre, to pixels on the ground, imaging spaces as small as 30 centimetres. They're also capable of imaging the landscape in stereo, from which we can derive three-dimensional models of what the landscape looks like. And increasingly, we're using that idea of capturing data moving beyond a two-dimensional map to actually quantify how the landscape is structured in 3D, and then how it evolves over time, if you like, moving towards four-dimensional maps, how landscapes change. And we do that using techniques like 3D laser scanning, and now it's possible to cast not just an 80-metre window on the world, or even a 30-centimetre window on the world, but now we've got data sets that are actually capturing thousands of points per metre squared, showing us what the structure of the individual gravel particles look like on the bed of the river. So, an amazing raft of new technologies at our disposal to understand how the system is behaving. And that's given us the ability, in a sense now, to shine some new perspectives on questions which are essentially old. And I wanted to give you 3 illustrations that are pertinent to the system we're looking at here today. The first relates to how much sediment is generated in these catchments. Yeah? how much sediment is generated by the erosional processes that I say are so aggressive in this environment. Can we quantify that using these technologies? Second, where does that sediment go and how do the rivers respond over what I'm going to call centennial timescales? So that's over something like 50 to 100 years. And then what are the processes that control the rate of sediment transfer through the environment and how do these rivers adjust in floods? Okay, so these are three coupled questions, if you like, yeah, giving us an idea of how much sediment are we generating, how's that affecting the rivers over the long term, and then what are the processes driving the evolution of rivers flood by flood. So for the first question, one of the projects I led here over the last decade has been to try and understand one of the key drivers in the system, which is the effect of landsliding. And I'm sure many of you will remember that on the 5th of January 2014, there was a major landslide up at HORO or slipstream up in the headwaters of the Dart that was significant enough to actually impound the river during a flood at a peak of around about 800 cumecs that was registered down at the hillocks there. And actually, you can see the river suddenly doing these little adjustments, dropping out its flows, dropping out again, as the debris waves that were coming down from that landslide pinned the river back and created what was then New Zealand's newest lake, about a 4.5 kilometre lake, actually filled up to around about 4.5 million cubic metres behind around about a 10-metre dam that formed at the base of the debris flow here. Now, my colleagues from GNS Science flew out, as they like to do, go and grab a helicopter, disappear out and do a quick risk assessment. And they concluded that there was no major risk of a dam break flood because the height of the dam was relatively low. But they estimated that around about 1 to 2 million cubic metres of sediment had come down in that one single event. Now let me give you a figure for reference. The average amount of sediment we think comes down through the Dart in any 1 year of coarse material is about 300,000 cubic metres of sediment. So at 1 to 2 million metres, we're talking about 3 to 6 times the average amount of sediment passing through that system in a year. Well, that's an interesting hypothesis. Can we do a little bit better than just turn up on site, wander around with a GPS and try and get those estimates? Well, one way we can do that is to use these next generation of satellites. And we can develop photogrammetric models, the highest resolution models of the Dart River system that have been produced here yet to date, by taking images from 2 different perspectives from those satellites, matching them up just as our eyes do, and reconstructing the 3-dimensional depth of the landscape. And this has allowed us to develop around about 0.5 metre resolution models of the whole catchment of the Dart. At the same time, we got up in some helicopters as well and took some photographs of the whole system from the headwaters down to the bottom. And using both the satellite imagery and our own helicopter surveys, we constructed a timeline of how this system up at HORO has evolved from 2007 to 2016. The key period of interest here being the dates around the 2014 landslide. And so this gives you a nice 3D model of what the landslide looks like. But what we can do now is go one step further. We can take away our data straddling either side of these dates around the landslide and actually take the 2 3D models away from each other and compute how the landscape has actually changed vertically. And the model that you see here, coloured in reds and blues, the reds correspond to areas where the landscape has gone down, i.e. it's been eroded. The blues are where that sediment has been filled into the landscape or deposited at the foot of the landslide here. And you now get a sense of the scale of the erosional processes that we're looking at. So right up at the headscarp here, if you take a cross-section from A to A dash here, we've got widespread areas where there was up to 20 metres of scarp erosion at the top of that landslide. But as that large source area was then captured by gravity and conveyed down through the landslide complex, it scoured out an extremely deep scar on the landslide you can see here, where the rates or the actual magnitude of elevation change is up to 70 metres. So it was scarred out. All that material was accumulated at the top, being pushed by gravity down through the system, scouring out roughly here around about a 300 metre wide channel that's of a depth of about 70 metres. And as that material then gets loses its gravitational power as we fall onto the fan here, large amounts of it has been stored on the debris fan surface here, and you can see that the fan has actually risen by around about 15 metres. So the scale of this event is extreme in any geomorphologic perspective. We can then begin to quantify what that actually looks like. We can measure how much material was in the source area of the landslide, how much then got stored on the fan, and you can do a little bit of maths here to actually compute how much was generated at the top, how much got stored on the fan, and therefore how much didn't get stored and ended up in the river. And you do the maths, it turns out that it wasn't 1 to 2 million cubic metres of sediment in that landslide. There's actually 17 million cubic metres of sediment in that landslide, of which around about 6.8 million cubic metres got stored on the fan. That meant 10 million cubic metres plus ended up in the river. Okay, so this is the first time we've really been able to quantify just how significant these kind of events are. And you know that HORO isn't the only complex like this in the REES-DART catchments. Muddy Creek on the Rees, all the debris flow systems that are in the upper Rees and in the upper Dart are capable of generating large volumes of sediment like this. But these one-off extreme events can be resetters for a system. They can be major sources of material, and we should expect our rivers to respond to these one-off events in quite unpredictable ways. So, how is the river responding? Well, I'm not going to talk about the response from that one event. Let's go a little bit further back in time now. So I've said that we now have an unparalleled archive of environmental change. Our Landsat series of satellites date right back to the 1970s, and we've got the first images from space of the basin here shown you in this image from 1973. And we've constructed a timeline of information here from the Landsat satellites that go all the way from 73 to 2019. Now these satellites are a little bit cleverer than our eyes. They can not just see the red, green and blue light we put together to produce our own multicoloured images in our brain. They can actually see light through the near infrared and even into the thermal infrared, capturing a lot more information about how the surface materials, the vegetation and the rocks are reflecting light back to space. That lets us do some clever things. We can apply some algorithms that actually try to learn what those patterns of reflection look like, and then we can use those algorithms to classify the pattern of land cover that we see in each of those satellite images. And at a very simple level, we can break down the pattern of land cover here into 4 different categories. The wetted areas, so the areas that are actually inundated with water in the river channels at one particular time. The amount of exposed gravel, so these are areas of gravel that are unvegetated. Taking those 2 areas together, we can actually map out where the active channel bed is. So this is the area where we expect on individual floods to become active and to be regularly being overturned. In addition, we can map out parts of the gravel bed which are being partially vegetated. So these are areas where the vegetation patterns of succession are beginning to set seed, and we're beginning to see vegetation encroach onto the gravel bars, or indeed areas where existing islands have been disturbed and sediment is being overlaid on top of them. And then there are also parts of the valley floor which are essentially stable, which are either laid down to pasture or forest, but are essentially evidence that they've not been disturbed in that recent past. So we can construct a timeline of how the system is varying now in terms of the active areas of the channel bed, the areas that are disturbed or stabilising, and the areas that are inactive over the last 50 years. And the pattern that emerges is quite striking. So back in 1973, we can see the active corridor of the Dart and the Rees Rivers here mapped out in red. As we move forward in time, stepping in between these images to 1990, 2001 and 2019, you can see that the channel is actually shifting its location through time. And between 1973 to 2019, you've got a more or less east to west migration of the whole delta front during that period. Pattern of just 50 years. It's also a little bit more subtle. You can see some extra patterns if you begin to quantify what's happening if we break up this system as we move downstream. and we can map out the pattern of the active belt as we go from the delta front here all the way up to about 40 kilometres upstream here, and I put some markers in the system here. This is where the river contracts at the hillocks, where it contracts again just above Paradise, and where it opens out at HORO here, to give you a bit of context. And the dates mapped here, the fine dotted line is 1973, the large dots are 1990, the solid blue line 2001, and the solid red line 2019. Well, I'm not going to go into too much detail here, but alongside that long-term migration of the lower delta from the true left of the valley to the true right, what we also see is that there's been a pattern of expansion followed by contraction of the active gravel bed. And that active area has expanded and contracted by around about 200 metres, or not far off 15 to 20% of the active channel belt as we've gone downstream. So for example, if we have a look down here at the delta, in 1973, the fine dotted line, you see that the delta then expanded into 1990, then contracted back to 2001 and contracted again to 2019. Similar pattern of change we see here upstream as the river widens out before it gets to the hillocks, and a similar pattern of change in between the hillocks and Paradise. So the river seems to have been a little narrower in 73, grew wider in 1990, contracted again to 2001 and contracted still to 2019. The exception being the major expansion of the river associated with the big landslide in the system up at HORO or slipstream between 2001 and 2019. So this is a river which is not just restless in terms of where it is, but the active river valley is actually contracting and expanding over time as well. And indeed, it's a sensible question to ask, where is the river? Okay, this river doesn't stay in one place. The river is actually probably best thought of in probability terms. What we can tell you is where the river never goes, which are the green areas here, where the river has always been in the last 50 years, which are the areas of red, and then in between that we've got the transitional areas, areas where the river has gone once or twice and is gradually coming back from stable towards a transitional environment, and where the river is gradually also going in the opposite direction from active towards stabilising. And this gives us a very good basis for understanding how we might, if you like, zone the appropriate land uses that we might put to pay on the river valley floor here. But put another way, I think it's really important to think about making space for the river to adjust in this way. We cannot control the river and put it in one place. Its natural tendency is to occupy a much wider area than you see at any one point in time. The river you look at today is a snapshot. It's responding to that variation in sediment supply that we've seen from upstream. Okay, let's go down a time scale and think about the individual floods. So the very first project we set up here on the Dart River was actually to try and use some new technologies. Something's, that's not mine, luckily. Some new technologies to try and really get down into the detail of what this river looks like. And we played some games. We set up our own little amphibious craft here, which had a laser scanner on the top of it, a laser scanner which we could navigate. So we had a GPS and an optical camera system on here that we could navigate around the bed of the Rees River. And we worked for a period of a year to construct really detailed 3D models of what the river looked like in between and after a series of 10 floods that came down through the river during 2009 through to 2010. We did this over a relatively short reach of the river. The state highway bridge crosses here on the Rees, and the river, the distance from here to here is just around about 2.8 metres here. So it's a relatively short reach, but when you look at the complexity of the environment here, this shows an image which is capturing each of those 10 different terrain models flickering through time. And the metaphor I like for looking at a braided river like this is that it's a little bit like watching fire. Yeah, it's never stationary, it's always flickering. It's statistically similar over time, but the active channels are always migrating. They're shifting back and forth, redistributing the sediment as that material is being transported by the floods and moving downstream. Now, we've used those data to give us some really detailed insights into the character of the river, by which I mean its form and structure. We've also been able to quantify how the river has changed, flood by flood, and then we've used those data to begin to construct. Is this going to play or not here? Let me just do something. Are you going to play or not? We've also been able to use those data to begin to develop some numerical models, he says. These things never play when you want them to, do they? Oh, sorry. Okay, being able to use these data to develop some numerical models that predict how the flows of water transport sediment and then produce these patterns of erosion, the reds here and the blues, we can now mimic numerically through a series of computer algorithms that capture the physics that control the movement of water and sediment through that system. And the image you're seeing here is showing you the time series of how the river is responding to 4 floods during that sequence. So we're able to take observations, convert them into information about how the river is responding, and then use that information to convert it into numerical models that allow us to predict how the river will respond to floods as they move through time. And this gives us, in a sense, a virtual laboratory that we can begin to conduct some experiments upon. That little virtual laboratory, we can feed in synthetic discharges. What happens if the river flows increase? What happens if the sediment supply to the river increases? How will the river adjust over time? Now, we've been able to do quite a lot with that data set, you might imagine, but some of the simple messages I think are useful to focus on as well. This process we use to try and analyse how these models of the river change through time is what we call DEM differencing. Sounds complicated, but it's pretty simple. We create a digital elevation model, a DEM of the river, before a flood and after a flood, and then we take one away from another and we can produce a map of the 3-dimensional pattern of change. By doing that, we can quantify the volumes of erosion and the volumes of deposition in the environment. We can also calculate the change in the mean bed level of the river. Is the river going up or is the river going down? And then we can map it out in extreme detail here. So this is a 0.5 metre resolution model. Every 0.5 metre we can see whether the river's going up or going down between 2 floods. And some of the information that we can generate from that at the very coarse level is pretty phenomenal. About 71% of that reach, so nearly 3/4 of the area, either underwent a pattern of erosion or a pattern of deposition during that year. Okay, 78% of the riverbed, therefore, was disturbed at one time or other during that river. So there's very little of that bed that was left unscathed during that 1 year. This riverbed is more or less constantly in motion. Now you go to the Rees today and about 5% of it will be inundated. Yeah, you know, I'm sure you've all crossed the State Highway Bridge, that in flood it all looks inundated. Yeah, well, virtually all of that energy is capable of transporting material at one time or other, so that the reach is actually undergoing repeated patterns of erosion and deposition in individual locations, disturbing the environment over wide areas of the active riverbed. When we begin to break down, we can actually begin to measure how much work, if you like, how much sediment was transported in the individual events, and then we can come up with some very simple little numerical rules to tell us how the river was responding. And one of the things we were able to do here is actually construct a very simple statistical model of how the river transports its material in response to the intensity of the flood that was driving it. And it turns out that the rate of sediment transport increases extremely predictably with the intensity of the driving flood. So we're able to work out what are the essential parameters that cause sediment transport in the system, and they turn out to be extremely predictable. There is more or less a linear relationship between the intensity or the power the flood has and the amount of bed load, the coarse sediment that can be moved by the river. Well, that's really quite an unusual result. Okay? Most rivers don't behave like that. Most rivers have an intrinsic threshold beyond which sediment gets moved. Yeah? The Rees River is more or less unlimited in its capacity because the total available sediment is unlimited. Any increase in the transport capacity increases the power of the river and the ability to carry material downstream. Well, what does that mean then? Well, the important take-home message here then is that increases in flood frequency will lead to a direct increase in the rate of sediment transport. Most rivers don't behave in such a simple way. So despite all of the complexity that you see out there, in actual fact, the pattern of behaviour of this braided river is paradoxically quite simple. And paradoxically lets us get at some quite simple ways to predict how it might behave in the future. Okay, apologies for delving into some of the detail there, but let's backtrack and think about some of the lessons hopefully we have learned. The first is that sediment supply is high, no surprise there, we probably knew that, but what we've learned is that it can be dominated by these large extreme events. What does that mean? Well, it means that we should expect that pattern of variability over time to be quite extreme as well, punctuated by large events like we've seen at Slipstream here. And it's not the only one in the catchment, remember. There are plenty of these processes driven by extreme landsliding going on in the Upper Rees and the Upper Dart. What does that mean? Well, it means that we should expect sediment supply to vary over time, and that should affect the pattern of downstream channel stability. Because as that material is fed into the system, it will destabilise the existing channel structure that's there. Second, we need to make space for our rivers. Yeah? It's not appropriate to look at the river today and think it will always be there. The rivers are shifting mosaics of landscapes. They are continuously migrating across the valley floor here, filling it up over time, and it does that, filling it up by spreading the material from one side of the valley to the other and back again. Our insight into how this river behaves is a very, very myopic little window on how that river behaves, and in even just 50 years, we've seen the river move from one side of the valley to the other. We should then expect the active river corridor to expand, contract, and migrate over timescales of the order of decades. Finally, sediment transfer is essentially transport limited. Okay? What does that mean? Well, it means that if there are increases in storm frequency and severity, they will directly impact on the rate of sediment that's being transported from the headwaters to the outlet down here at the delta and into the lake. Okay? Three quite powerful messages that I think underpin how we need to understand this landscape and how we think about its management into the future. Okay, I will finish off with some lessons that can help us think about the way in which we can also use some of the new technologies that we've looked about, some of the new methods to help try and inform management. And one of the key things that we've done in one of the other projects that we ran out of the back of these studies into HORO, the REES and the DART, is helping the regional council, as well as other regional councils, the United States Geological Service, the US Army Corps of Engineers, the UK Environment Agency. We've worked with a whole host of river management agencies around the world to try and help them use some of these new technologies, such as airborne LiDAR surveys, and turn that information into valuable geomorphic data to help underpin how we manage our rivers. And we've done that with the Regional Council here by developing a software suite which allows them to take in these new generations of 3D models of what our rivers look like. We can fly aircraft over our rivers, scan them now with lasers moving underneath them to create really detailed models of what our river systems look like, and using the technologies that we've talked about, difference those models over time and show how the landscape is evolving. Now, our airborne LiDAR surveys for the REES-DART areas stretch back to 2011, at which time the Regional Council commissioned a small survey just of the Delta area here. And then as we go forward into 2019, a larger survey was redone and occupied all the way up just past the hillocks here on the Dart and up to Lover's Leap here on the Rees. And these provide really powerful data to understand how the landscape has changed during that period. We can use those technologies to compare one model against another to then actually calculate how the river bed level has been changing over that time. So down in this lower delta area, we've taken the 2019 model, subtracted the 2011 model from it, and then the pattern of change you see here, the reds are where the river's gone down, the blues are where the river's gone up. Okay, so you see that really phenomenally complex mosaic of different landforms as the river has migrated, and you see this large areas of right bank erosion that are now beginning to tax and challenge the road here on the way out from the hillocks to Kinloch. And then we also see large areas of sedimentation at the confluence of the two rivers. This was an area that was opened up in 2015 and has now begun to really infill as we move towards 2019. And then there's the Delta Advance at Kinloch here. John will be able to tell you lots about that. It used to have a lakeshore view, now has a view of some gravel bars in front of Kinloch. Yeah? This is an environment which is changing. What we can also do with that now essentially is put a cross-section, not at every 500 metres or every 2 kilometres, we can put a cross-section across this river every metre now and actually understand how the river is changing continuously and come up with some really reliable data on the pattern of erosion and deposition as you go upstream towards the delta front. And if you look at the Dart River, the pattern is pretty stark. Yeah, this is a river which is building up its sediment as we move towards the delta front. The figures here probably aren't too easy to read here, but essentially where you see the red colours here, this is where there's an average pattern of erosion corresponding to this major channel change that occurred here upstream in 2017. The other areas where you see the blues here are where the river has been degrading. And typically, in the lower parts of the Dart Delta here, we see that the channel has been building up by around about 15 centimetres over the last 8 years. Doesn't sound like a lot, 15 centimetres, does it? But if you start adding 15 centimetres in 8 years, then 16 years, then 24 years, that pattern of aggradation really begins to build up as the channel bed is on average lifting up. The pattern on the Rees is even more extreme. So we can do that pattern of bed level change here. We've averaged that now at 250 metre intervals as you migrate upstream here. And the pattern, as we do that, we can map out the erosion, which should be showing here as the patterns of red. And if our river was in equilibrium, we would expect as much erosion as we see blues for sedimentation. What we actually see is a system which is entirely dominated by aggradation. The riverbed is lifting up. The rate at which it's lifting up is consistent, more or less, throughout that whole lower 5 kilometres, and it's going up by around about 20 to 30 centimetres in that 8-year period. So about a foot in old money, where I come from. Yeah, the river's been lifted up by about a foot in that lower 5 kilometres over the last 8 years. Extrapolate that over 50 years, yeah, 1 to 2 metres of bed elevation gain. That's a significant loss of flood capacity as we move forward over a 50-year time horizon. So, we can begin to see evidence of that by looking now. This is a little walk I took upstream here, June 2020, following the big flood that occurred in February the 4th, earlier last year. And now you can look at actually large areas of the left bank of the Rees, where the gravel bars are more or less at the same height as the floodplain surface. Geomorphologically, we call that the freeboard. Basically, how much capacity has the river got before it can jump out into the floodplain and find a lower route downstream. And we've got significant losses of freeboard all along the lower reach of the Rees here, and significant areas where the Rees is actually continuously popping out and beginning to erode that bank and also spread its sediments over the floodplain as well. So, a system which is dynamic, a system which is changing, and a system where, with all that available sediment, we can only expect that pattern of change to continue into the future. So I said there are good reasons to assume that the fluvial hazards will increase. Let's put a little bit of detail on what we mean by that, and then I'll wrap it up. Okay? I think there are 4 mechanisms by which we've got to think about these fluvial hazards becoming more significant over time. The first is in the form of riparian erosion. Erosion of the existing areas that we treat as stable. That's the distance from the river to Kinloch Road, yeah? Down to a matter of metres in some areas now, yeah? A little bit of armouring is not going to stop a river which is capable of flowing at 1500 cumecs, yeah? That's a pattern which is makeshift for the time being. A pattern which we have to understand is going to be challenged because as the bed level continues to rise, that increase channel bed level will cause the individual channels of the braided river to migrate more rapidly. And as they migrate more rapidly, the lateral migration will impinge increasingly on the outer edges of the channel belt and begin to erode away at the assets that lie alongside it. So we should expect increased bed levels to increase the pattern of riparian erosion. Where it happens will not be consistent through time. There will be hot spots, and those hot spots will migrate. At the moment, as the river has shifted east to west, Kinloch Road's taking the brunt of it. Over a similar 50-year time period, punctuated by patterns of upstream sediment supply, we can expect the river potentially to migrate back and forth across that channel bed. So the hot spots of where riparian erosion will occur will vary. But we've got good evidence for understanding where the stable parts of the system and where the dynamic parts of the system are now. The second process driving fluvial hazard is a loss of the existing levels of service of the stock banks that do already protect the town. So there is a QLDC supported, I think, I'm not going to go into that, who built stock banks here. Let someone else talk about who built stock banks. Yeah, there is a small stock bank that protects the northern limits of the town. Okay, that stock bank was built and designed when the river was significantly lower. Yeah, the river bed has been rising, as we see, at around about 30 centimetres over an 8-year period. Yeah, potentially of the order of a metre in 50 years or more. That will put increased pressure on the outer bends. What that will do is it will increase an individual flood will now reach a higher level on the river. So the same discharge will now reach a higher level because the riverbed has come up. The higher level will impinge upon that bank, creating increased pressure on the outer bends, but also increasing the hydrostatic pressure from the river to the areas on the floodplain. And what that can do is it can create the formation of little pipes of water seeping underneath the stock bank, bubbling up on the leeward side of the stock bank, which is only really here built of an earthenwork construction. And if that occurs, we get the potential for a catastrophic breach of the stock bank. Well, that's only likely to occur where the river is hard up against the stock bank, so that's probably now in the lower 250 metres of the Rees as it impinges hard upon that stock bank close to the delta front. Third, increasingly problematic issue that the community is going to need to think about here is the potential for backwater flooding associated with the Rees essentially being diverted up Lagoon Creek. So if the Rees is beginning to fill up its channel bed here, we're reducing the capacity for flood flows and reducing the gradient of the river. That will mean that the ability for the water to go this way in floods will decrease. It will find another steeper route, will be flowing up Lagoon Creek, as well as stopping any flows coming down Lagoon Creek at the same time. What that will do is it will push water all the way up here till it gets above some of the low points in the existing stock bank protection. Now, the height difference between the mouth of Lagoon Creek and the top of the lowest points in the stock bank up in the near the dock bridge there is less than about 1.5 metres. Okay, it's very, very possible for the flows to push up to that height, and then, as happened on February the 4th, overtop the stock bank up there, and then begin to run through the lower margins along the northern town here. This is a great big fan itself on where the township's being built, be rerouted along the northern margins of the town, here, along the edge of that fan, inundating the properties that you see here. Now, those kind of processes will be, should have put that, shouldn't I? Overtopping the stock banks at its low points. Those kind of flows will actually probably be relatively slow water events. They're probably not going to produce significant fast or swift water flooding, but they could produce depths that may reach in some parts of the town well over 1 metre. Yeah, so they will pose a significant hazard, not just to property, but potentially to human life as well, if we aren't able to provide appropriate mechanisms of evacuation. So, what is the one that worries me most? Well, I guess this is the one that worries me most. And that is that there is an elevated risk, I would argue, of severe outbreak flooding. Now, we've seen in the last couple of years evidence of this occurring in 2 different river systems, not necessarily great analogues for the REES-DART, but equally not that dissimilar in many ways. The first of those was the Waiho River in March 2019, and then a little bit later in the year, the Rangitata did a similar thing in December 2019. What do I mean by an outbreak flood? Well, we've already seen that there are areas where there is significant loss of freeboard, some way upstream in the system. So not close to the township here, but some 5, 6, 7, 8 kilometres upstream. That significant loss of freeboard potentially means that the flood could get rerouted along a steeper path across the floodplain. And we call that process an avulsion. So this is essentially the river no longer being able to continue down its traditional route. It then finds a steeper route over the floodplain and takes an alternative way downstream across areas of productive land, but potentially also overwhelming the stock banks that are currently protecting the northern areas of the town. That will produce pretty significant swift water movement through areas of the township. So we're not talking now about the nice gentle rise and fall of a backwater flood or the rise and fall of the lake, but potentially a significant component of the Rees flowing directly towards the township. Now, if you want a good illustration of what that looked like for the Waiho, well, in the immediate aftermath of the Waiho flood in March 2019, we went out, took our own airborne LIDAR, we flew the system from the glacier right to the coast, and we were able to map out all of those patterns of channel change, comparing LIDAR models of the system in 2016 and then LIDAR models in 2019. And you can see what happened at Milton Stockbank. This is where the Waiho overtaxed and breached an existing flood defence. The river then was diverted all the way across the southern floodplain here, finding an 8 kilometre, and this is around about a 700 metre wide route, not just flowing across farmland, but actively eroding it, destabilising it, submerging the aerodrome in sediment, submerging roads and the paddocks of all the farms down here. Luckily not the individual farmsteads, they were better placed, but essentially the river retook part of its natural floodplain. And I think that's the point to learn here, yeah? We live in an environment where you see the river today is not where the river has always been. It's been shifting across this it's drifting across its valley floor over long periods of time. The capacity for an outbreak flood like this is a significant event. Where would Glenorchy be? Yeah, is a question that you need to ask. Glenorchy could well be, right in the path of an outbreak flood like this. So there's a significant question that we need to contend with in that threat to the township here. When you look at the existing LIDAR data that we can now use to visualize these processes, this is a model which we call a relative elevation model. So this is not simply the absolute topography. What you see here are areas that are high and areas that are low of the valley floor relative to the height of the riverbed. So anything that's green is essentially above the mean height of the river. Anything that's blue is below the mean height of the river. So we see, for example, the intricate and the particularly highly eroded right bank channels of the Dart that are impinging upon the western margins of the valley floor there. But what you also see is large areas of the Rees, which are what we call super elevated above the surrounding floodplain topography. The Rees is essentially depositing its sediment within the active channel. That's causing the active channel to rise to the point whereby the Rees actually becomes considerably higher than the floodplain off to its left. We don't know when, where or how an outbreak flood could occur, but there remains a significant chance that as the river begins to fill up these areas, that at some point or other, freeboard will be lost and there is the possibility for rerouting of flood paths down toward the lagoon here and in areas where there is currently limited stockbank protection. Certainly, if a major component of the Rees was rerouted in this direction, those stockbanks would be ill-positioned to afford any defence against a major. Sorry?
That happened this time.
I don't think it happened this time. I think what happened this time was this. The main flow of the Rees was backed up, pushed the flow up along Lagoon Creek.
No. It came over the bank and we followed it.
Well, so did I. And
we were standing in it when it came over the bank at the golf course.
Oh yeah.
And it flowed all the way down the inside of the bank.
Oh yeah, absolutely.
And went from, hit the hit the pole house, and it was
Yeah.
like a river running.
Down through here. Yeah.
Yes, because we'd lived in the floods going back at us for years.
Yeah.
So this time it actually flowed over the bank and down the inside of the bank all the way to the house. There was no water at the house.
Absolutely agree. Absolutely agree.
So that didn't happen this time.
Now that what happened this time, I think, is that the flow of the Rees was backed up along Lagoon Creek. It then
There was no
over.
water on the inside of the flood bank.
Sorry.
There was no water on the inside of the flood
No,
bank.
it's Lagoon Creek, but Lagoon Creek was actually flowing from east to west.
Yeah, there was no water
It
from
was.
here all the way up to the golf course on the inside of the flood bank. So it came
No,
over.
that's not what he's saying. But what he's saying is that the creek was flowing the other way around, but it wasn't. It was flowing from east to west because when before it broke, just like about 2 minutes before it broke through the golf course, I was at the house that is on the platform just on the right of that arrow that is turning towards Lagoon Creek, and I ran to the flood bank, and it was flowing from east to west, but it was about this much under the top of the flood bank.
Lagoon Creek.
Yeah,
Lagoon
yeah,
Creek,
it came
yeah,
over
it
the
was
top.
from east to west, absolutely.
So where's the
Flowed
source of
all
the
the way
water
down.
that came over the top then?
It was the Rees somewhere upstream.
Yeah, the reef's coming up the further up the valley, by Irish
Yeah.
Scots Waves,
Yeah.
and flowed like exactly what that map
That
said.
picture you took.
It actually happened.
That's what happened.
Well,
So this
That's
time
what
around,
they look like.
that map was perfect. That's
Sure.
what happened. So that's happened now.
sure. Okay. I wasn't there. I don't know. Yeah. There are two mechanisms that could have caused what we saw happening in February.
I
yeah?
can understand where you're coming from.
One is backwater
Yep.
and overtopping.
We've seen that.
Yeah. The alternative is
That one. That's perfect. That's what happened.
And
this
that's
time.
what happened. There was
That's
lots
exactly
of
what happened.
freeboard up near the Scots,
Sure.
and then it came through like a gold race, elevated into the lagoon. Because of the lowness of the flood bank, it just overtopped it,
Sure. Yep.
and then it came through. And
I think
that's
both of
all
these
right.
are the
Yeah,
mechanisms.
well, I don't know you
Someone
knew that
have
it
to
happened.
look
On what your research you've done is that map there. I thought, you've done it on the last flood, and you're saying that this could happen in the future.
Well, this could definitely happen. in
Well,
the
this is
future,
what this is.
Could be good
That's
on this.
exactly your data is correct because that's what happened.
That's what we like to
No,
hear.
no, it's bang on. It's bang on.
What I will argue is that what you saw come over was a relatively small amount of the Rees.
No, we went from nothing at the house to a river this deep within a matter of 5 minutes.
And how fast was the water flowing?
Fast.
Okay, all right.
Like it was a flowing river. So that
If that's
data
the
there-
case, then I
The
stand
water-
corrected.
The water came in, according to that mechanism, into the lagoon, but because the Lagoon Creek was blocked and it was coming up against the Rees as a liquid dam,
The backwater effect.
the backwater effect. So that did happen. It stopped it from getting out.
The
So it
point
came
is
over
that
the bank.
these will happen together.
Yeah.
And the likelihood of that happening in the future is very high.
And what's significantly at risk
That
here
green.
is that if you lose more and more of the Rees going this way, then that stock bank won't be a little
That's
bit
our really
overtaxed,
concern
it will
now
be
because it's
significantly overwhelmed.
It's heading to the eastern side of the town where the old channel goes through the golf club, and that's an old channel. And we're scared that it's going to come through there and go through the Camp Glenorchy, down that shit. So that is bang on what you've done. So I can tell you now that from what we need to do, what can we do from now since you've got the data, that was perfect. And that's what happened this time around. So it's not one of the things that are going to happen in the future. It actually did happen. It happened this time around, and you predicted it pretty well.
But you've got to remember that this is now just going to get worse, isn't it? Yeah. And the lesson that we're beginning to see here is that in a system which is essentially unlimited in terms of the amount of sediment coming down into the system, this is one-way traffic now. The river is only going to continue to erode. There's no reason to assume that this is going to flip back into an erosional state.
So yeah,
Nearly there.
we thought it needed a break.
That's fantastic. And you know what? I absolutely, I was not there on February the 4th. Yeah. The evidence that we had was that the water flow was relatively slow. Yeah. If it wasn't, then that worries me more.
Like it was a fast,
It
a really
It was a
fast.
flash
evolving.
Like we got there 5 minutes, it went from your foot to your waist.
That would have been interesting to know.
Yeah, well.
Anyway, I'll leave you with those conclusions and let just open to questions. Yeah, because we've obviously covered a lot of ground now. I'm very happy to go back over anything that we've talked about. I hope you found that useful as a little bit of background context. Hopefully it sets the scene for the discussions tomorrow, which are really an opportunity to gain your insights into the justice we've been learning about here, and to think about what might be the appropriate approaches to take to manage these hazards into the future.
It'd be like Venice, wouldn't it?
Well,
Move the town up onto the hill.
yeah, interesting question. Okay, well, I'll leave that there. Has anyone got any questions? Things you'd like me to go back over?
You know, it's very seldom one has the privilege of listening to such high quality presentations. Thank you. And I can see the effort and the resources that the Otago Regional Council put into it. And again, it's great to see ratepayer money being used to such great effect. There's a difference between how you see it, the ORC, and the QLDC. So what's happening to align the two councils? Because as ratepayers, we fund both. And if we get a lawsuit, as is happening in Waiho at Franz Joseph, of a hotel suing the regional council for $30 million, that $30 million doesn't come from anybody but the ratepayers. So how do we protect ourselves? And first of all, it's going to be with the ORC, you sound convinced. The QLDC is absolutely hell-bent on development, it seems to me. And so how do we bring those two things together? Because at the end of the day, we're going to be left to pay the bill. We can't insure. So I, for one, am very worried about having to pay my part of $30 million, which is something real that's happening now on Waiho.
Yeah, look, and I don't have the answer. This is a political question, but I mean, I think,
No, it's a real question.
No, it is.
The issue, the political
think
thing
that-
is how people work out what the answer is.
Well, we can have a chat about that, Bruce. In fact, Kate's got some good thoughts on that, but it's probably not the scientist's one to answer. It is political. Kate's suggesting, what are you saying?
Look, the regional policy statement is coming out. The new regional policy statement is coming out. Consultation.
Pretty soon.
End of June, I think.
End of June. And that is the top policy statement that councils can have of where things should happen, and then it will include comments about where you should be putting residential developments, which are seen quite differently from commercial and everything. Jean-Luc has a huge feed-in of data that he feeds to that. That's something you can submit on, but also the Queenstown Lakes District Council, whenever they do any reviews, is also where he will give information about that and say you need to be keeping an eye on this. But the regional policy statement is the best one that you can say we shouldn't be allowing residential or further residential development where there may be this sort of risk.
Yeah, and
Or commercial.
there's another layer on that as well with the National Policy Statement for Urban Development, where regional councils are now compelled to work with territorial authorities such as Queenstown Lakes to identify the most appropriate areas for urban development. So you've got that bubbling away as well. So we have a mandatory responsibility to get alongside such as Queenstown Lakes.
Is that what your June meeting's going to be doing, that sort of thing?
Sorry?
Is that the sort of thing you'll be discussing at your next meeting in a few months' time?
Yeah, so one adaptation aspect is through planning rules and changing the district plan, for example, could allow or is allowing here.
So will you be using this great data that we've got here now, which is brilliant?
Yeah.
Are you guys implementing this into what you're doing?
Yeah, so that'd be one aspect.
So this year,
Tomorrow we'll be talking about those kind of levels. So either changing the
so this is gold
land use. Sorry.
This is gold stuff there.
Yeah.
For especially in our situation. So it'll be great to see you using it. And if we don't hear you using it, that'll be
No. The other thing I want just to add to that is we're working closely with QLDC now on that project. So tomorrow we'll have people from QLDC coming also to discuss. So we're trying to align on what we know and what each council will have responsibility to, and QLDC will be involved in land use planning, but also infrastructure, clean-up road, what the future of that. So those things are definitely part of that adaptation project that
we're here to talk about.
I guess there's distinguishing the two. There's how do you not make a bad place worse? So controlling future development. I guess it's all about the existing development and the existing occupation. So will you be looking at both of those aspects?
Yeah.
I've got a non-political question.
Fantastic.
No, so I've got a question about, you were talking about the glaciers receding and releasing a lot of sediments. Now, do you have any models regarding that because of like the impact of climate change on the actual presence eventually of the glaciers of the valley? Will there be a moment when there will be a stop for sediments to come in such big numbers, or do you have any models about that? Do you have
Do
any
you mean in
data?
terms of the rates of glacial retreat?
Yes, and how does that impact the sediment release?
Yeah, I don't have any forecasts on the patterns of retreat of the existing glaciers that are left, other than to say that these are essentially extremely stagnant rumps of what was once there. Yeah, I think in terms of the overall.
So meaning potentially most of the sediments have already been released.
Most of the sediments have already been released.
Yeah.
Yeah. What has become clear through a lot of research in this catchment, but as well as others in the Southern Alps, is that it's probably not the glaciers receding now, liberating sediment that's the modern control, it's landslide. It's actually, most of these systems are being driven by the high rates of sediment supply from landslides and debris flows.
As you said, it's very steep, so
It's over steep and it's tectonically active. These landslides occur both as a result of shaking, but also just in heavy rainstorms, sometimes even without any rain or seismic trigger. Yeah, they can fail without
just gravity.
Hey, thank you for your presentation. I've listened to it. Nevertheless, I'll re-ask a question. I mean, what do you say to those people that would still seek like a stop bank solution, maybe right around GLENORCHY? Bearing in mind, and I'm aware that there's a risk from the Rees, there's also a risk behind the flood bank, so be careful what you ask for, all this type of stuff. But nevertheless, that question's going to be asked, in terms of what would you say to them?
So this is a semi-political question. The answer is that we can always build flood defences at some level. Yeah. The danger of building flood defences in the event of an environment where you have a shifting baseline, as in we have increasing frequency of floods, increasing severity of floods, and an increasing rate of sediment transfer, is that you need to keep checking those defences with that changing background environment. I was at a meeting about the WIHO earlier last year where NZTA revealed that they had constructed plans that indicated the maximum height you could build the stop banks around the WIHO to, and the answer was 17 metres.
Yeah.
Right?
So
that's not a stop bank, that's a dam.
So you're exacerbating the risk profile.
You are exacerbating the risk profile. You're elevating property prices behind it because you're creating an illusion of security.
Yeah.
You're also elevating the potential risk that when an event does overtop that system, you've got more people in harm's way and more property in harm's way as well. Now, that's a decision ultimately though that rests with the community is the way I would approach that. What we can do is use the science to help inform some of the decisions that you guys get to make.
But potentially you can do some stuff that buys you time, so that you can adapt.
I think
that's probably
if
community
what we're
message
hearing
would be that not all going to change overnight, is it? People aren't going to change where they live or where we build or whatever overnight. So there will be some.
So look,
time
for example, what we've heard this evening is that some of the mechanisms that we think of as worst case scenarios are already beginning to pan out. Yeah. I think there are possibilities to mitigate some of those events in the short term. They might not necessarily be the right long-term solution for the community. That's a decision for the community as well.
I've got one question. I remember when you first started doing the survey, I was an installation at the time, up at the Rees. Now, can you remember the groins that put up there that the river had naturally...
On the Rees?
On the Rees River, where you come out through the Narrows behind Camp Hill there was a series of probably 4 or 5 groins that were you would have seen them all the way down. And that there was implemented by the river itself. on a just initial small, with some groins coming out. Now, over time, have you ever looked at, has there any been data done on that? Because it was Tommy Thompson back in the day that it was a simple way of using the material that was coming down, putting it into a place where it built up, and then keep the reefs back over towards the other side there. And over time, those groins have further up, what the narrows there, they've just disappeared over time over floods and that, and now the river's sort of just doing wild things. Yeah. For a while, that was under control for quite a little bit of the time. Do you do anything on that? Or is it just natural sort of progression of this equation you've put together?
So I think
or is it old school
engineering? Yeah, maybe. Groins have historically been used in lots of rivers to do two things. One, to deflect the river away from
that's what it
valuable asset, but also in the hope that by narrowing the river, you increase the rate of sediment transport. And,
so that's what they would
make the river dig down.
Yeah, that's all they knew. They didn't have this technology.
Well, that pattern of making the river dig down by narrowing it works quite effectively where the river is sediment supply limited, as in that it's got more transport capacity than the sediment that's being charged through it. These systems are not like that. So if you narrow down the river, all you're going to do is cause more sedimentation. You cause more sedimentation, you're going to overwhelm the groin.
Because that's protected that road for 25 years. It's never come down that side again. It blew the flood bank out. It was this northern flood bank, and then they did that. And it's been settled for a long time now. So
I think there's haphazardness as well here, because it hasn't gone there doesn't mean it won't.
Yeah, well, that's right. Yeah. Mother Nature can kick her ass any time. That's basically what she can do. So that's not awesome.
You mentioned that slipstream had a fluid amount of sediment, which measured, I think you said, about 11 million cubic metres was the fluid.
Came down into the.
Over what period of time did that move?
Oh, that came down within less than a year. So that's
From
most of. Oh, how far has it got down into the system?
Yeah.
We don't know the answer to that. I mean, I think you probably find that a large amount of fine material was evacuated quite quickly, and is probably being evacuated as we.
But essentially, that's a period of a year.
There is potentially quite a legacy of large coarse material in the upper reaches. And certainly, as I walked up there earlier this year, it seems to me that there's evidence that the river is degrading quite rapidly in that reach from slipstream down towards China.
Sounds like a lot of material, but what you're saying is that moved from slipstream itself in 1 year.
I think
to somewhere.
Oh, I think that's coming down. I mean, it's now 5 years since the event, 6 years since the event. That material is moving downstream. I think is a reasonable hypothesis. How significant that will be when it starts to widen out and gets down into the reach, south of Chinaman's, the river widens significantly. It will buffer that wave of material moving through. So it's probably not going to lead to particularly rapid change in the next 5 years or so down at this end of the system. It might take decades to work its way all the way through the system. And we're seeing those kind of decadal shifts in the river expanding and contracting. My hypothesis is it will probably take that order of time before we really begin to see that wave of material down here.
Okay. Given what you've described, one of the solutions suggested is managed retreat for GLENORCHY. What does management retreat look like to you?
Well, that's a big question. I think there are probably multiple stages to that. I mean, there are certainly areas of the township which are more directly in the firing line than others. And we've seen, you've seen the February the 4th flood. Essentially is creating a kind of conduit of flow around the northern margins of the town, because this is a large built-up alluvial fan, a fan which has largely been built from sediments coming out of the Buckleburn. So it's convex in shape. The lower margins of that are around the northern perimeter. So where would I not want to buy a house now? Where would I be more comfortable buying a house? Well, then I'd have to think about all of the other risks that the township faces. So there are significant issues associated with liquefaction which are not going to be settled by moving from here to here. So I think there's not one catch-all answer for that. I mean, there are broader risks that need to be part of this equation, not just the river. But certainly the higher up the system you are, there are some pretty large areas of flat, expansive ground where the town could resettle if it was as radical as that. But a push southwards would certainly alleviate the risk of this kind of event for some of those.
You mean the south north, mate?
Yeah, we'll be turning through rivers.
Away from here.
But that other side there where you're going, I know you suggested about where the old dumper is, the gravel way that comes down through, that's right behind the cemetery there, before the Buckley.
Yeah.
These are great conversations for tomorrow.
We're off track, sorry.
The short answer, I don't have an easy answer to that. I mean, I think part of this process is engaging with the community to hear your views on what you think appropriate solutions to manage retreat could look like. What we can do is help inform that with some of the science that can underpin those decisions that you make. That sounds like, again,
yes, that's exactly tomorrow. That's the start of the discussion, and the next session in about 6 months, that'd be the core of it. You know, what retreat could mean, or other options. But that's really, the next step, using what James has described today, but also what James just mentioned, other hazards. We're not only talking about flooding, and James had that map initially showing all the possible sources. So how we can take that into account, this information, to build an adaptation plan and pathway for the area.
If people want to share this video, is this going to be available?
Presentation.
Yes.
Yes.
Yeah, we'll try and put it up on our website, the web page for this project, and then a copy of the slides as well. We'll share. So yeah, everything will be available.
Excellent.
sorry, some questions.
Will you be here tomorrow, Jen?
I will.
The community find itself in a rock and a hard place really, because the council's just asking for submissions on its 10-year plan, and they want to be carbon neutral by 2050, but there's actually no steps in the next 10 years to achieve that. So, you know, the community finds itself in an extraordinarily difficult place of waking the council up to the fact that climate change is real.
Sure, sure.
And
I think some of the impacts of climate change are signed off, yeah. So some of the adjustment that's coming is already built into the pattern of pattern of urban development and anthropogenic global CO2 emissions over the last 150 years. Yeah, it's not something that we're going to offset now. So we've got to prepare for patterns of climate change which are already happening and will continue to occur over the next century. We can potentially, as a global community, offset some of the worst ravages of that if we do things quickly, and that's precisely what the Paris Accord and all of the the transitional changes that we need to make economically, socially, and culturally are about. But they're global questions as well as local.
yeah, they're global and local.
Yeah, they are.
Council's
Yeah,
choosing
I
to-
absolutely agree.
Yeah.
You need action on all scales.
Submit.
Sorry.
You sort of answered my question, but people might be interested in hearing this anyway. But Bruce and I walked REES-DART at REES-DART, and my eyes have saw this over the eyes. I saw a number of quite deep-seated subsidences in the headwaters in both the Rees and the Dart, Snowy Creek in particular. And I found myself thinking, there's a huge rainfall event. These are all going to become active like slipstream. There's going to be a huge increase in sediment into the Dart, into the both rivers. I found myself asking the question over Easter, what would be the approximate travel time if these few million cubic metres go into the headwaters, between them getting from there to there? I think you've answered that because it's just a river carrying capacity, but it's not just slipstream.
I think
that whole catchment is.
It's a spot-on question to ask. I remember going on a field walk with a community group in California, and someone turned around to me and said, "Well, if I throw this rock in the river, how long is it going to take to get down, to the Golden Gate?" And it's a fair question, and it's one where geomorphologically the answer to that is really difficult, because what we see here is a system which kind of does things in leaps and starts. Yeah, not like a flood which moves through at a constant rate. Material gets stored and then remobilised, stored and remobilised, stored and remobilised. So the pattern of transfer of material from somewhere like slipstream down to the delta here isn't going to take place in 1, 2, 3, 4 events. It's going to take place over decades. Yeah, part of the system will, however, be responding very quickly. Yeah, but
might it be visible as a lump in the sediment coming down, moving down river?
Yeah, there's evidence certainly in other places that you see sediment waves adjusting like that. So you see more or less a bed wave moving downstream. That's a hypothesis that we haven't tested in this particular system, but it's a good one to have a look at. And that goes back to this question I was saying about what, there's definitely, to me, visually, evidence that there's sediment build-up between slipstream and Chinamans. Yeah. What happens as that gets buffered, as it moves out into an area where there's greater potential for accumulation between Chinamans and Paradise, will slow down that process. Yeah, but it won't stop the process. So speed will not be constant over time, but that sediment wave is likely to migrate downstream.
Did you come across any other ones like you've seen in the past before this one? Any indications in the mountains of that happening before?
Well, the Waiho is a classic example.
Like is there history? There probably will be history of slips up the valley there.
So the Waiho towards State Highway Bridge rose by 8 metres over about a 30-year period. Yeah. It looked like it had begun to crest, and that pattern had ceased to rise quite so dramatically in the last 5 to 10 years. But the last big flood that occurred in March 2019 brought an extra 3 million cubic metres of sediment into the top end of that system, and the top end went up by 8 metres. So there's every reason to assume that process has been going again. It's a really challenging question to understand how that process occurs.
What's the time? Sorry, just ask what's the life left in the Rees Bridge based on the.
So there's guys who are eating at this stage.
Write it down.
Haven't looked at it.
But do we actually have data on how much the level of the sedimentation has risen under the bridge?
I don't have any data that I've looked at recently to point to.
You would have remembered when you could walk under there and drive a car, drive a horse under there, but you were now.
So, ORC's perhaps not talking to QLDC about that particular piece of infrastructure?
One thing that's one really powerful tool in the armory is that you now have LiDAR surveys from 2019 that extend all the way up valley. Yeah. One of the problems we have with this analysis that I showed you is that we're really looking at a very narrow portion of the system. To understand how the system here is going to respond, we need to be looking all the way upstream. The beauty now is you've got a baseline which is really beginning to project up far enough upstream to make some sensible insights into how the system as a whole is behaving. Yeah. So when we did that analysis on the Waiho, we were able to go right from the glacier terminus right down to the coast. Yeah. There's every possibility that we can redo that kind of analysis here, and the possibility to collect those data gets cheaper over time, the quality of those data get better over time, and you can get much more into an active form of management, where you actually got real-time information to help you design appropriate management strategies and think about questions around gravel extraction, stock bank construction that could provide some short-term solutions to help the community.
Just one more question whilst we've got the staff and the councillors here, because there's funding on. In terms, we've got no flow gauge information on the Rees. We've got a lot on the Dart, but we know that the catchments are different. Is the funding there for that? For a flow gauge on the Rees?
Obviously, with the regional council guys the other day, they haven't got one.
This one. Have we got the funding?
It's in the long-term plan that's going to be released for consultation shortly.
Tomorrow.
So yeah, tomorrow.
Okay. So it's included.
It's proposed as an action within that.
Okay.
What year?
I don't remember. It's probably year one.
I think it's year one.
Okay.
Yeah, so we put the second lake level recorder in, and we'll put a, like an early year 1, 2 suitable site. Put in.
And it'd certainly be a valuable source of information, that's for sure, because there is significant differences between the pattern flow records, as you guys will know, between the Dart and the Rees, and therefore that information would seriously help you with some planning. Okay.
Thank you.
Thank you very much, everybody, for coming along this evening. And hopefully we'll see you tomorrow for more discussions, because that's where we have a chance. A lot of the councillors are up here, so you can have those productive discussions as well. I'll see you tomorrow.
What do you mean?
Yes.